Welcome you all for the another lecture on process calculation and unit operation. So far we are seeing about the unit operation, mixing and agitation. So for any unit operation, the ultimate aim is we need to have a less power requirement, because all these unit operations are mechanical operation which requires a motor which has to be function. So for functioning of this motor, we need electricity or some kind of power in order to make this motor to run. So for this we need to calculate the power requirement, because the power requirement is going to be more than 50% of the cost for preparing this unit operation. So whatever the unit operation it may be, whether it is size reduction, whether it is mixing, whether it is a filtration, whatever it may be, the major cost for developing this unit operation is going to be more than 50% is for power requirement. So if we are going to invest more amount of money on power requirement, then the ultimate unit operation what we have developed is not cost effective. So in order to make your unit operation as a cost effective, we need to develop we need to minimize the power requirement in order to make it as a cost effective one. So we are going to see how to calculate the power required for a unit operation, and we are going to see how to calculate this power, and then how to minimize this power in this lecture. So we will get into the lecture. So to calculate the power required for a agitated vessel, the agitated vessel is nothing but it is the vessel in which you are going to carry out the mixing process. So in this vessel, if you are going to operate, then this vessel has to be operated using a part called impeller. That impeller has to be connected with a motor. So if you are going to operate the impeller, or if you are going to carry out the mixing, then the motor has to function, and if the motor has to function, then we need to supply the power. So we need to calculate what is the power required. So for calculating this power requirement, we need to have one thing called power number, and then Reynolds number. So these are the two things we need to know in order to calculate the power required for a agitated vessel. One is called power number and another one is called Reynolds number. If we know these two numbers, then we can able to calculate the power required for an agitated vessel. So power used in agitated vessel. So as I told, in the design of an agitated vessel, since the power requirement for a agitation is going to be cover more than 50% of the cost, it is an important factor is the power required to drive the impeller. So what we are going to have is, we are going to have a agitated vessel. In this agitated vessel, we are going to have the mixture. This mixture is going to get mixed using a part called impeller. So this impeller is you will be operated using a part called motor. So this motor will be connected to a power. So in order to have a mixing, we need to rotate this impeller. In order to rotate this impeller, we need to operate this motor. In order to operate this motor, we need to supply the power. So we need to calculate what is the power required for the operating this mixing operation. So empirical correlations have been developed to predict the power required. So many scientists have worked and they have developed many correlations, and using these correlations we are going to find what is the total power required for a proper mixing of a liquid. So that's what we are going to calculate. So the first number what I told is called the Reynolds number. So Reynolds number is a number which will tell you the flow behavior, how the flow is going to happen, whether it is slow and steady, or it is like a flood like flow is going to come, or whether a silent flow is going to happen. So what kind of flow is going to be that? So the Reynolds number will tell you what is the flow behavior of a particular liquid. So if you are calling your Reynolds number that is of less than 2000, then your flow is going to be steady and silent, and this type of flow we call it as laminar flow. And if your Reynolds number is going to be 2000 to 4000, then it will be of some oscillations in the surface of your liquid flow, then we will call it as transitional flow. And if it is going to have many eddies, and if you are going to come as a very vigorous flow, then the Reynolds number is going to be more than 4000, and we call it as turbulent flow. So based on this Reynolds number, we can tell what kind of flow is going to happen in your liquid, whether it is a Reynolds number, or whether it is a laminar flow, whether it is a transitional flow, or whether it is a turbulent flow. So for Reynolds number 2000, less than 2000 flow is laminar, 2000 to 4000 it is transitional, greater than 4000 it is turbulent. So this is how we need to identify the flow of a liquid using the Reynolds number. So to calculate the Reynolds number, we are going to have a formula called NRE is equal to rho Vd by mu. So this is the actual formula to calculate the Reynolds number, but in case of mixing, we are going to have a different form of this Reynolds number, that is NRE dash. Instead of NRE, we are going to have NRE dash. This is Reynolds number for mixing. So this rho Vd by mu is going to get changed into this diameter of the tank is going to be converted into diameter of the impeller. D will be converted into dA square, then N rho by mu. So dA is nothing but impeller diameter, N is rotational speed, rho is fluid density, and mu is fluid viscosity. So this N is going to be revolutions per second, and diameter is going to be in meter, and rho is going to be kilogram per meter cube, mu is going to be kilogram per meter second. So these are the unit system we are going to follow, and this is the formula to calculate the Reynolds number for mixing apparatus. So next what we are going to see is about the power number. So as I told, we are going to have two numbers, one is Reynolds number and another one is power number, in order to calculate the total power for an agitation system. So one is the Reynolds number that we have seen, and next one is called the power number, and this is the formula to calculate the power number. NP is nothing but this is the power number, that equal to P is nothing but total power required for the agitation, and rho is density of the liquid, N is the rotational per second, and dA is the impeller. And this is in case of your SI system, and this is in case of your FPS system. So depends upon the unit system that has been asked, we are going to use the formulas. If it is asked in an MKS system, that is SI system, then we are going to use this one, and if it is going to be asked in FPS system, we are going to use this formula. And the unit for total power is joule per second, or we can use it as watt. So these things we can use it and we can calculate the power number. So first thing what we need to calculate is the Reynolds number. So step to calculate the total power P. First step is we need to calculate Reynolds number, and then second step we need to calculate the power number. So to calculate the power number, we should know what is the total power, but our ultimate aim is to calculate the total power from the power number. So to calculate this power number, we are going to have a new relation called power curve. Okay, so this power curve is going to relate the Reynolds number with the power number, and you are going to have the curves. So using this curve, we are going to calculate what is the power number. So once you calculate the power number, you have to calculate the power using this formula. So this is how we need to do the problems and calculating the total power for a mixing apparatus. So this is the power curve. So this is called power curve. So using this power curve, we are going to calculate what is the power number for a particular Reynolds number. So first we know how to calculate this Reynolds number, NRE dash. Once you have calculated this Reynolds number, we need to identify what is the power number. So this power curve is going to be plot between NP versus NRE dash. So your x-axis is going to be NRE dash and your y-axis is going to be power number. And the scientists have developed several curves. These are called power curves. So these power curves are unique for each and every impeller type. 1, 2, 3, 4, 5, 6. 6 types are here. This 6 types is for each and every impeller. So this is for 6 blade impeller, and this is for flat, this is for open type. So similarly, different types of impeller will have different types of curves in this power curve graph. So in this graph, we need to identify what is the impeller type, and then we need to select the curve. Suppose if our impeller is going to be 6 blade impeller, then we need to select this Reynolds first curve. So using this first curve, we need to identify what is the power number. Suppose our Reynolds number is going to be 10 to the power of 3. So 10 to the power of 3, we need to draw a straight line vertically, and then it has to cut at the first curve, because first curve is going to be our impeller, and then where it cuts, we have to draw the horizontal line and we need to identify what is the power number. So for 10 to the power of 3, for 6 blade impeller, the power number is going to be 4. So like this, we need to identify the power number for the each and every corresponding Reynolds number. So using this power number, we can able to calculate the total power required for the mixing. So if you see here, this up to 10, this is going to be laminar. In case of your mixing Reynolds number, the Reynolds number is 1 to 10 in the sense NRE dash is less than 10, it's going to be laminar. And if it is 10 to the power of 4, transitional, and greater than 10 to the power of 4, it is turbulent. That is, this to this is transitional, and this is called turbulent. So this is how we need to use the power curve. So this power curve will be given in the exam itself, or we have to bring the separate graph sheet, that is this power number and Reynolds number graph, and we need to identify the values, or the values will be directly given in the problem itself. So how to use this power curve? Power curve is a graph between the power number versus Reynolds number for mixing. So once you know calculated this Reynolds number, we need to identify the power number using this power curve. So power curve will consist of different curves. Each and every curve will be unique for each and every impeller type. So we need to first identify what is the impeller type, and then we need to select the corresponding curve. So if it is going to be 6 blade impeller, then we need to select the first curve, and then the corresponding to the Reynolds number, we need to identify what is the power number, and using this power number, we need to calculate what is the power required. Using the formula, power number formula, we need to calculate what is the total power required for the agitation system. So this is how we need to do the problem. So as I told you, in power curve, we have different types of curves. So in the example what we have seen, we have 6 curves. So this 6 curves is going to belongs to, first curve is going to be flat 6 blade turbine with disc, and curve 2 is going to be flat 6 blade open turbine, and curve 3 is going to be 6 blade open turbine, curve 4 is going to be propeller, and then curve 5 is going to be propeller, pitch is equal to dA, and then your curve 6 is going to be high efficiency impeller. So likewise, each and every impeller type is going to have a different curves in case of your power curve, and using that curve we are going to calculate what is the power number for the corresponding Reynolds number. So using this formulas, using these formulas, we are going to solve one problem in order to calculate the total power for agitation system. So what we need to do is, first we need to design the agitated vessel using the specified impellers and all, and we need to calculate what is the power required for the mixing apparatus. So for 100% mixing, what is the power required? So suppose the power requirement is going to be huge, then the process is not cost effective. Then we need to change the impeller type. Then if you change the impeller type, then the power curve what you are going to select in your power graph is going to get differ. So you have to optimize such a way that you have to select an impeller that will correspond to the lower number of power requirement. So this is like a trial and error method we need to do, and we need to select the impeller, and based on the impeller we need to select the curve in the power correlation curve, and using that curve we need to identify the power number, and then we need to calculate the total power. So when you are going to get the 100% mixing with low power requirement, then that is a good unit operation for mixing. So using that mixing operation, you can use you can mix the liquids for 100% effectively. So based on this, we are going to see one problem, and we will solve, and we will try to know how to apply these formulas to calculate the total power for a agitated system. A flat blade turbine agitator with disc having 6 blades is installed in the tank similar to figure 3.4.3. The tank diameter dt is 1.83, the turbine diameter is 0.61 meter, dt is equal to h, and the width w is 0.122 meter. The tank contains 4 baffles, each having a width of j of 0.15 meter. The turbine is operated at 90 rpm, and the liquid in the tank has a velocity of 10 centipoise and a density of 929 kg per meter cube. Calculate the required kilowatt of the mixture. For the same condition, except for the solutions having a viscosity of 1 lakh centipoise, calculate the required kilowatt. So this is what given the problem. So first what we need to do is with the data, we need to find out what is the Reynolds number. So using the Reynolds number, you need to go for power curve and you need to identify what is the power number. And using the power number, you need to calculate what is the total power. This is how you need to calculate for this first subdivision. And in the second subdivision, instead of 10 centipoise, it is going to be 1 lakh centipoise. So this thing you need to change it in the second subdivision and you need to calculate what is the total power required. So the relation you have to you please note down the relation between the centipoise and kilogram per meter second. So 1 Pascal second is equal to 1000 centipoise is equal to 1 kilogram meter per second. This is the one relation, and another relation is here it is given as revolutions per minute. So this per minute we need to convert it into seconds. So 1 minute is going to be 60 seconds. So this also we need to convert, and this centipoise also we need to convert into kilogram per meter second. So we need to convert these two things and then we need to find out what is the total power required for this agitation system. So these are the given data in the problem, and as I told you, n is equal to 90 and we have to convert into seconds. So for this we are going to have 1.5 revolutions per second, and mu is going to be in centipoise. We are going to convert it into kilogram per meter second, and rho is given the problem. First we are going to calculate what is the Reynolds number. So Reynolds number is going to be dA square n rho by mu. So when you substitute, this is going to be 5.187 into 10 to the power of 4. So using this Reynolds number value, we are going to find out what is the power number. So for calculating the power number, you need to go to the power graph. So this is the power graph. So the value is 5.187 into 10 to the power of 4. So first we need to go to the 10 to the power of 4, and in this 5.187, this is 5.187, and the curve type or the impeller type what we have is the 6-blade impeller. As per the problem, we have 6-blade impeller, so we have to go to the first curve. So 5.187 into 10 to the power of 4, this is the place, and this is going to be constant value. So if you draw a vertical line to this and if you draw a horizontal line to this, you are going to have a power number of around 5. So we need to check with the problem what is the value that they have got. So power number what they have got is 5. So NP is going to be 5. So using the power curve, they have identified the power number value as 5. So dA by W is equal to 5 and dt by J is equal to 12 and NP is equal to 5 and NRE dash equal to 5.187 10 to the power of 4. And using this, they have calculated the power number as 5. When you substitute in the power number formula, they have calculated power as 1.324 kilowatts. So similar to the previous subdivision, instead of 10 centipoise, if you replace with 1 lakh centipoise, you can obtain the total power requirement as 3.71 kilowatts. So if you increase your viscosity by 10,000 fold, but the power requirement is going to be only two-fold or three-fold increase. If it is going, your viscosity increased by 10,000 fold, your power requirement will be increased by only two-fold or three-fold. So this is a very effective process, because the viscosity, if it is increased, then the requirement will also increase with a large number. But in this case, in this impeller type, if your viscosity is going to increase by 10,000 fold, your requirement is going to be three-fold increase. So this is what this is how you need to solve the problem, and you need to get the total power requirement for a agitated system. So next topic what we are going to see is about the scale up. Scale up is nothing but from a small size we are going to prepare, or we are going to make a bigger size. So smaller size in the sense, normally we have three types of scales. One is called lab scale, and another one is called pilot scale, and third one is called industrial scale. Pilot scale, lab scale is going to be the very smallest one, and the pilot scale is going to be the medium one, and your industrial scale is going to be the larger one. So if your reactor is going to be less than 6 liters, then it is going to be lab scale, and if it is of 20 liters to 100 liters, then it is going to be pilot scale, and if your reactor is going to be more than 100 liters, and if it is of 1000 or 10,000 or 1 lakh liters, then it is going to be industrial scale. So using these scales, we are going to mix the liquids. So if you are going to scale up from your 1 liter to 10,000 liter, then what is the dimension of the agitated vessel that we need to follow. Suppose if you are going to have a diameter of the impeller and the diameter of the tank of the different ratios, then what is a ratio that we need to follow for the 10,000 liter. So if you directly scale up from 1 liter to 10,000 liter, it will not be helpful. Then we need to scale up with the corresponding increment in the size. If your impeller diameter is going to be 1 for 1 liter scale, then it should be of some value that is correspondingly to the 10,000 liter. Then only we will have the same kind of 100% mixing in both the scales. Otherwise, if you are going to increase with the different dimensions, then you will have 100% mixing in case of your 1 liter agitated vessel, but in case of 1,000 liter agitated vessel, you will not have 100% mixing. So for this purpose, we are going to have a topic called agitator scale up. So in this scale up, we are going to have a ratio called scale up ratio. So using this ratio, you can able to convert all the dimensions from the smaller one to the larger one. Suppose if your impeller diameter is going to be 1 meter and your scale up ratio is going to be 10, then your diameter of the impeller for a 10,000 liter is going to be 1 meter for the small scale into scale up ratio is going to be 10. 1 into 10, that is going to be 10 meter. So your 1 liter and then 10,000 liter, these are the two things that you are going to have. For 1 liter, impeller diameter is going to be 1 meter and your diameter of the 10,000 diameter of impeller for the 10,000 liter you do not know. If you want to find that one, you need to have a relation between these two things, that is called scale up ratio. So this scale up ratio value, say for example, if it is going to be 10, then how to find out this diameter of the impeller for the 10,000 liter, in the sense diameter of the impeller for 1 liter into scale up ratio, that is going to be your diameter of the impeller for 10,000 liter. So 1 liter, say for example, if it is going to be 1 meter and scale up ratio is going to be 10, then 1 into 10 is equal to 10 meter is for your diameter of the impeller for your 10,000 liter size. So this is what we are going to calculate, and for this scale up ratio we are going to have a derivation to calculate the formula. So to arrive at a formula, we are going to have a derivation, and based on this derivation, based on this formula, you are going to calculate the scale up ratio, and based on this scale up ratio, you are going to find out the new dimension for the new scale, and then also to calculate and also you are going to calculate what is the total power required for the new scale also. And whenever you are going for this scale up, you are going to have something called reference. Suppose if you are going to find out some unknown things, you need to compare it with the some standard ones. So similarly, if you are going to scale to a new size, you need to have a small reference size. That reference size we call it as standard agitation system. So for standard agitation system, the geometric proportions are fixed. Geometric proportions in the sense the dimensions. So what is the length, what is the breadth, what is the diameter of the impeller, what is the diameter of the tank, all these things will be fixed, and the ratio and the relation between one to the another will also be fixed. If you see, the diameter of the impeller and diameter of the tank should be equal. Diameter of the impeller and the height of the liquid surface from the bottom should be equal. So like this we have different relations that should be of common and should be followed throughout, and when you are following these dimensions, then that agitation system is going to be standard agitation system. So as I told you, this is called standard agitation system. For this we need to follow this kind of geometric proportion. dA by dt is going to be 0.3, with this ratio is going to be in the range of 0.3 to 0.5, and h by dt should be equal, that is its ratio is going to be 1, and c by dt is going to be 1 by 3, w by dA is going to be 1 by 5. So similar to this we have different kinds of relations, and if you follow these relations, then we are going to design some agitation system, then that agitation system is going to be called as standard agitation system. So for next what we are going to see is about calculating the scale up ratio. So suppose for example, if you are going to have 1 liter, you are going to scale up to 1000 liter, then for calculating the new dimension, suppose for example dA is the diameter of the impeller and this is the dA for the new dimension, new impeller diameter. So if it is going to be 1 meter, you do not know what is the dimension, but what we need to follow for this 10,000 liter. So to calculate that one, we are going to have a relation called scale up ratio. So to calculate the scale up ratio, if we, for example, if it is going to be 10, then 1 meter into 10, that is going to be 10 meter, is going to be new dimension for the impeller diameter. So this is how we are going to follow. So to calculate the scale-up ratio, we are going to follow this derivation. So scale up the laboratory size or the pilot size agitation system to a full scale unit. The full scale unit is nothing but it is the industrial unit. So this is the scale up procedure. First what we need to do is we need to calculate the scale up ratio. As I told you, this relationship we need to calculate first, this scale up ratio. So this we call it as R. Assuming that the original vessel is standard cylinder. So as I told you, the standard cylinder is nothing but we need to follow some dimensions that has to be given the standard geometric proportion. So here they have taken as diameter of the tank is going to be height of the liquid surface from the bottom. This is the geometric proportion they have taken, and the volume is going to be. So normally the agitated vessel is going to look like a cylinder. So the cylinder's formula is going to be pi r square h. So this is in r, if you write it in the terms of d by dt square by 4h. So this is what they have written here, by dt square by 4 into, sorry, this pi r square h, pi r square h. So pi dt square by 4 into h. So since we have taken as a standard cylinder, dt1 is going to be h1. So in this dt1, instead of this h1, you are going to replace it with dt1. Then the formula will become by dt1 cube by 4. Similarly, for the second reactor, if you write, v2 is going to be pi dt2 cube by 4. And if you take up a ratio between v2 to v1, then we will get dt2 cube by dt1 cube. So the scale up ratio is going to be r is equal to this one, this power 3 is going to come here, v2 by v1 whole power 1 by 3, that equal to dt2 by dt1. So this is what the formula for your scale up ratio. If volume of the two reactors 1 liter and 10,000 liter is going to given, then what you need to do is, suppose for example this example if you are going to take, then the volume of the second one is 1000 liter, volume of the first one is going to be 1 liter, and you need to put 1 by 3. So this is going to be your R value. Similarly, if diameter of the tank is given, then you need to take the second new vessel's diameter of the tank divided by the previous one's diameter of the tank. So if you take up a ratio, that will be the scale up ratio. So as I told you, once you calculate the scale up ratio, what you need to do is you need to multiply the previous one dimensions with the scale up ratio to obtain the new dimension. Say for example, if you want to get the new impeller's diameter, then the previous one, smaller one impeller's diameter with the scale up ratio you need to multiply. Similarly, width of the baffle if you want to get, then you need to multiply the width of the smaller size baffle then with the scale up ratio. If you multiply, then you will get the new one's baffle width. This is in case of all the dimensions, but it will be differ in case of your rotations per minute, revolutions per minute. So if you are going to calculate the agitator speed for the new one, then the relation or the formula to calculate is n2 is equal to n1 into 1 by r whole power n. So instead of multiplying r directly, you are going to take an inverse and then you are going to raise the power to n. So this n is nothing but it will be differ and it will be depends upon the expectation that you are going to meet. Suppose in smaller size if you are going to have 1 liter and you are going to have 10,000 liter. This 1 liter and 1000 liter should have a same liquid motion, that is whether the laminar flow, if it is going to be there in 1 liter, the same laminar flow should be there in 1000 liter, then you need to substitute the n value as 1. Suppose if you are expecting some equal suspension of solids, if it is of 90% solids has been suspended, the same 90% has to be suspended in case of a 1000 liter, then you need to substitute the n value as 3 by 4. Suppose if you are expecting some equal mass transfer, then in case of your 1 liter and 1000 liter, then you need to substitute your n value as 2 by 3. So if you substitute all these n values, then you can able to calculate what is n2. So once you have calculated all these things, then you can able to calculate what is the power required for the particular system from this n2. So using these things, we are going to calculate a problem. An existing agitation system is the same as given the example 1a for a flat blade 6 turbine with a disc and 6 blades. The given condition sizes are dt1 is going to be 1.83 meter, da1 is equal to 0.61 meter, w1 is going to be 0.122 meter, J1 is equal to 0.15 meter, N1 is equal to 1.5 revolutions per second, rho is equal to 929 kilogram per meter cube, and mu is equal to 0.01 kilogram meter per second. So it is decided to scale up these results for a vessel whose volume is 3 times as large. Do this for the following two process objectives where equal rate of mass transfer is desired, where equal liquid motion is needed. So here the problem is given, you need to scale up this problem. What is the relation between these two sizes they have given is, first one is going to be, second one is going to be 3 times larger than the first one. This is the relation between these two things. Second one is going to be 3 times larger volume than the first one. So this is the relation that they have given. And also you need to substitute the n values. If you are going to calculate the agitator speed, then you need to substitute the n value as for two objectives, that is, one is for equal mass transfer and another one is for equal liquid motion. So for these two cases you need to substitute the n values and then you need to calculate the agitation speed, and using this agitation speed you need to calculate what is the power required for this agitator system. So these are the given data, and original tank volume is going to be V1 is equal to pi dt1 square by 4 into H1. So if you substitute these values, you are going to get 4.813, and V2 is going to be 3 times of V1. So 3 into 4.813, it's going to be 14.44, and R is equal to, if you, this is the formula, V2 by V1 whole by 1 by 3, then if you divide, you will get 1 by 3. Then if you, so normally what you will get, what you need to calculate is, you need to prepare a chart at the end. dt1 is equal to, this is first vessel and this is second vessel, dt1 is equal to, this is da1 is equal to, da1 is equal to, or we can call this da2. Then we have j1, j2, w1, w2. So similarly n1, n2, p1, P2, V1, V2, P1 by V1, P2 by V2. So like this, for the first vessel, what is the dimension, what is the agitation speed, what is the power? Similarly, what for the second vessel, what is the dimensions and what is the agitation speed, what is the power requirement? So all these things we need to calculate and we need to write up and fill up the values. So if you see here, we have calculated the scale-up ratio, and to calculate the new dimensions, we need to multiply the previous one with the scale-up ratio. So if you want to calculate diameter of the tank for the second one, then you need to multiply the diameter of the tank on the first one into the scale-up ratio. So the value for the first one is going to be 1.83, and the value for your ratio is going to be 1.442. So if you multiply, then it is going to be 2.64 meters. Similarly, you have to calculate for the other dimensions. And similarly for agitation speed, as I told you, n value you need to substitute as based on the expectation that you are following. For equal mass transfer, your value is going to be 2 by 3. This is what you are going to substitute, and when you substitute, you are going to get 1.175 revolutions per second. And using this thing, you are going to calculate the Reynolds number and then the power number, and then after calculating the power number, like the previous problem, you are going to calculate the total power required. Similarly, you need to follow it for the second vessel. So if you are going to see for the first vessel of smaller volume, it is going to be 1.324. When the volume is increased by 3 times, your requirement is also increased, power requirement is going to be increased by 3 times. But we need to see what is the power requirement per unit volume. So for every unit volume, what is the power requirement for these two cases? That's what we need to calculate. So if you calculate the power per unit volume, that is power per unit volume, that is you need to take up ratio of power to volume, then this is for the first vessel 1.324, and this is for the volume for the first one. If you take up the ratio, then you are getting 0.2752. Similarly for the second one, if you take up the ratio, the same value you are going to get. So power requirement per unit volume will be the same in two cases. Even though if you increase the volume by 3 times, your power requirement by unit volume is going to be the same. So it says that you are going to have a very good mixing in even though if you are going to scale it up. Similarly for the second case, that is equal liquid motion, you have to substitute n is equal to 1. So if you substitute, you need to calculate what is the power per unit volume. So if you substitute, you are getting 0.1909 kilowatt per meter cube. So if you compare this one with this thing, it is somewhat lesser. So if you are expecting some equal lipid motion, then it will require some lesser power for your larger volume of mixing. So this is what you are getting from this topic. So with this we are coming to the end of the fourth unit, that is agitation and mixing. So in this unit we have seen what is about mixing and what is the importance of mixing. What is the parts or the components of an mixing, what are the different types of mixing, and what are the how to design a mixing apparatus, and how to calculate the power number, and what are the different types of impellers available, and how to calculate the Reynolds number, and then how to calculate the total power requirement, and finally how to scale up from the smaller size agitated vessel to the larger sized agitated vessel. So far we have seen about the agitation and mixing unit operation. So with this we are concluding this fourth unit, and we will get back in the fifth unit. Thank you.